Welcome to the Problemers channel, season 3, episode 11, the episode which I titled A Point in Triangle Detection Algorithm, because in this episode we will discuss one point in triangle detection algorithm in detail. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the home page of this channel, and at the top of that page in the channel's trailer section find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section in that episode, and I will do my best in order to answer all of your questions. The challenge of the problem S3CS2 was to suggest several Turing machine-friendly algorithms for detecting whether a given point, let us say the point P, is located strictly inside or strictly outside of a given non-degenerate planar Euclidean triangle, let's say A, B, and C. Have a discussion of several such algorithms and discuss or implement one such algorithm in code. In this episode, we will first offer several honorable mentions for such algorithms, and then we'll deep dive into one such algorithm that can be coded directly without much specialized knowledge. Two popular branches of optics in physics are the so-called wave optics and ray optics. And both of these branches of physics study and attempt to explain the behavior, the properties, and the propagation of light using two different mathematical models. In wave optics, the model of light is taken to be the so-called wave or a wave front, and it is applicable to cases when the said light travels through obstacles that have their linear size comparable with the wavelength of the light under study. In other cases, in the so-called ray optics, a different mathematical model is used to describe the properties, the behavior, and the propagation of light through the medium. And that model is based on the notion of minimizing geodesic. And as one of the axioms of ray optics, it is taken that light, for example, from a point source, will propagate precisely along a minimizing geodesic. For example, the minimizing geodesic of a sphere will be a great circle, and the minimizing geodesic in Euclidean space is a straight line. And since in most cases the physical space around us can be modeled precisely enough with Euclidean space, and the flat surface, for example, can be modeled with the so-called Euclidean plane, it is taken that if a given light source emits a so-called ray of light, that ray of light will run precisely along the minimizing geodesic of the Euclidean space, and that is a straight line. Consequently, the basic idea of the so-called two-space ray tracing is to analyze the geometry of what is visible in the path of such a ray of light that is emitted by a point source. That is, more specifically, let us analyze the situation that we're given in the problem S3CS2. We're given, our algorithm will be given one point with which there will be usually 2 units of information associated, for example, the proverbial x coordinate and the y coordinate, and we're also given 3 vertices that presumably form a non-degenerate Euclidean triangle. And the idea of the two-space ray tracing algorithm for determining whether such a point is located strictly outside or strictly inside of a given non-degenerate Euclidean triangle ABC amounts to the following. Our given point has to deal with precisely 3 pairs of points. For example, we can even enumerate all these 3 points: the pair A, B, the pair B, C, and the pair C, A. Out of these 3 pairs of points that are distinct, and the points that define 3 distinct, essentially straight lines, our point P can be collinear with one and only one such pair. For example, let's say our point is collinear with a straight line that passes through the points A and B, and in that case that point will be not collinear with the straight lines that pass through the points C and A and C and B. As such, the idea of the two-space ray tracing method of determining whether the point P is located strictly outside or inside of a given non-degenerate Euclidean triangle amounts to computing the midpoint of any of the sides of a given triangle with which the given point is not collinear. That much should be evident because that is the only case where this idea works and makes sense. For example, we compute the midpoint between the points C and B, and this point comes out to be right here. Then we construct precisely a ray of light that emanates from the point source, which is the point P. We make this ray pass precisely through the midpoint of the chosen side with which our point is not collinear, and then we simply count the number of times that such a ray, when it runs into infinity, will intersect all the sides of the given triangle. Then from this straightforward visual experiment, it should be evident that if our ray constructed as I explained intersects all the given sides of the given triangle an even number of times, then what conclusion do we draw? Then in this case, for example, such a ray will intersect this side of the triangle and this one, for example. And extended evidently is the other one, but these two is enough. Then if our ray constructed as I explained will intersect all the sides of the given triangle an even number of times, then the point P is located outside of a given triangle. And if the ray of light that emanates from the point of interest P intersects all the sides of the given triangle an odd number of times, then the point P is located strictly inside of the given triangle. Here the underlying mathematics again is not too complicated at all. Nothing here steps beyond the typical, let's say, upper middle school or high school curriculum in terms of how much specialized mathematical knowledge a student must possess in order to comprehend the underlying mathematics. It's very straightforward, and judging by the number of CGI-based movies, let's say, that were made in the past, we can say that the two-space ray tracing method for determining whether a given point is located outside or inside of a given triangle is fairly Turing machine friendly, even though sometimes it can be said that when it comes to the real-time performance, that algorithm may not be very suitable. The second honorable mention algorithm, which can be used in order to detect or determine if a given point is located strictly inside or outside of a given non-degenerate planar Euclidean triangle ABC, is based on the following theorem. A point P is located strictly inside of a given triangle ABC if and only if the magnitudes of all three angles under which all three sides of the given triangle are seen precisely from the point P sum to precisely 2 pi radians. At this point, we recommend that our viewers put this video on pause, walk away from the computer, and try to generate a proof of this theorem on their own. Meanwhile, we will observe that for one direction for this theorem, the statement will be as follows. If the point P is located strictly inside of a triangle ABC, then the sum of the angles APB, BPC, and CPA will be precisely 2 pi. And the way we prove that statement is we basically do what's called angle chasing in mathematics. We use the Euclid's Elements Book 1, Proposition 32, according to which the magnitudes of the interior angles in any non-degenerate Euclidean triangle sum to what? To pi radians. That means that, for example, our angle x in the triangle APB can be represented as what? As pi minus the sum of the remaining two angles. This angle and this angle, shown with a wavy line. Here is 3 circular segments. And like so, the magnitude of the angle BPC, this angle can be represented as what? As pi minus the sum of these two angles right here. And the magnitude of the angle CPA, this angle, can be represented as pi minus the sum of which? Well, these two angles, this and this angle. Then in sum we will have 3 pi minus the sum of all these smaller angles, which precisely form the interior angles of the triangle. They sum to pi. We have the following expression: 3 pi minus pi is equal to 2 pi, and that is precisely what we have over here. That's in one direction. Conversely, our statement says that if the angles under which all three sides of the given triangle are seen from the given point P sum to 2 pi, then the point P is located strictly inside of the given triangle ABC. And here, for example, my idea is to, instead of fighting that particular statement, prove the contrapositive, which means what? Which means that if the point P is located outside of the triangle ABC, then the sum of these angles will not be 2 pi, and that is also very straightforward to prove, because in this case, let's assume for a moment that the point P is located outside of the given triangle. And we connect the point P with all the vertices, and what do we see? We see that the angle, for example, in this case, CPA and APB in their sum become also what? The magnitude of the angle BPC. And if we designate these two angles as x and y, then the sum of all these angles will be what? It will be 2x plus y. And if we temporarily assume that this sum is equal to exactly pi, 2 and 2 cancel each other out, we get this expression: x plus y is equal to pi. That means that the magnitude of this angle plus this angle is what? Is pi. The point P must belong to what? To the straight line that passes through the points C and B, it must be somewhere on that side, and that is precisely the case when the point is not outside the triangle ABC. This creates a contradiction and proves our statement, and it's contrapositive, which precisely says that if our angles of interest sum to 2 pi, then the point P is located strictly inside of the triangle P. Once that is understood, the mathematics here is nothing beyond a traditional upper, let's say, middle school, lower high school geometry curriculum. Nothing is very involved, nothing requires deep specialized knowledge. All we need to know that if the coordinates of the points C, A, B, and P are given, then the distances between all the points of interest can be computed in a trivial way using this formula shown over here. It's the square root of the sum of squares of the differences between the x and y coordinates of any 2 points, let's say A and B. That means that the distances of interest between the point P and the rest of the vertices and the distances between the vertices of the given triangle can be computed. And then for the angle of interest, we will do what? We will apply the so-called law of cosines, which says that, for example, the square of this side is equal to the square of this side, a plus b, minus twice the product of a times b, and times the cosine of the angle between them. Thus, our proverbial angle x will be given by this formula, arc cosine of a square plus b square minus c squared divided by 2 times a times b. All these distances, a, b, c, can be computed as shown over here. In the numerator, we're dealing with squares. C square, square, and square. We do not need the square root, but here in the denominator, we will apparently need to use the square root. And this is the first problem that shows us that this algorithm is very straightforward to comprehend. It's straightforward to come up with, to generate it. But when it comes to the real-time sensitivity and being Turing machine friendly enough, it is not Turing machine friendly enough. It is not performant when it comes to real-time path in our computations, because we will have to, for example, in the C runtime mathematics library, we'll have to call the function square root and arc a cos sqrt. These functions injected into the real-time path are too slow. This will be unacceptably slow. That's number one. And number two, when we compute all the magnitudes of all three angles, x, y, and z, for example, as shown over here, x, y, and z, we will have to sum them, and that number will be what? A floating point number or a double, and the straight comparison with the traditional equals operator is not going to work, because we will have to compare that sum to 2 times pi taken to a certain precision. That is another problem, that in our real-time path, we will have to inject the tolerance and write the test that captures the essence of the inequality shown here, so that our sum S must be within the small and narrow band of the number delta, and the magnitude of this delta is dictated by our sensitivity to the problem at hand. And that shows that this specific honorable mention algorithm for determining whether a given point P is located outside or inside of a given triangle is not very Turing machine friendly. The third and the final honorable mention algorithm that can be used in order to detect if a given point P is located inside or outside of a given non-degenerate Euclidean triangle ABC is based on the following straightforward theorem, which states that a given point P is located strictly inside of a given triangle ABC if and only if this time the sum of the areas of the three interesting sub-triangle, if you will, amounts to precisely the area of the triangle ABC, and what are the sub-triangles in this case? Well, in this case, the sub-triangles are constructed in the same way in which we constructed angles, the corresponding angles under which all three sides of the given triangle were seen from the point of interest P in the previous segment. The point P, the point P, and the point P, specifically taking the happy path scenario. The triangles of interest here will be C, P, A, again A, P, B, and B, P, C. If we cross hatch them this way, for example, this triangle will cross hatch that way. This triangle will cross hatch that way. A smaller triangle. This time we're dealing with not with angles, but we're dealing with areas. And the smaller triangle shown over here. And in order to prove this theorem, that proof you should try to generate on your own. It's not straightforward. We carefully consider four cases. First, when the point P is located outside, then evidently if we designate the sum of the areas of the three triangles in question as designated on the right hand side of your screen as simply S, as shown over here as a shortcut, uppercase S, then if this area is strictly larger than the area of the triangle in question ABC, then evidently the point P is located outside of the given triangle. Our algorithm should return, for example, false or 0. It is not the case that the point P is inside of a triangle. Again, here in this case we have a necessarily convex quadrilateral, and evidently the sum of the areas of all the triangles in question shown over here will be strictly larger than the area of the given triangle ABC. Next, we'll consider the case when the given point P is located on any one side of the given triangle. And in this case, what will happen? Well, in this case, precisely one triangle will be degenerate. The area of this triangle will be 0, and the area of the given triangle ABC will come out to be equal to the sum of the areas of the three triangles at hand, provided, of course, we understand the caveat that the area of one triangle will be precisely 0. In this case, what triangle will contribute 0 as its area? Well, evidently the triangle APB. Here we move the point P onto the side AB, and then the triangle APB becomes degenerate. Its area is 0, and though we have the equality between the areas of the given triangle ABC and sub-triangles, we carefully know that in this case, if these areas in question equal one another, but precisely one area of one triangle is 0, then we also return false from our algorithm. It is not the case that the point P is located strictly inside, and in this case we even can predict the point P sits on one of the sides of the given triangle, and we can even print out and deduce which side is that. Next case, we carefully move the point P into one of the vertices A, B, or C of a given triangle. In this case, evidently we will have the demanded equality, but the caveat is the following. In this case, when we move, let's say, point P into the vertex C, how many triangles will be degenerate? 2 triangles will be degenerate. Well, in this specific case, the triangle CPA, CPA, and the triangle BPC, since the point P, for example, precisely coincides with the vertex C, let's say, of our triangle. So in this case, when the equality of the areas is honored, but precisely 2 triangles contribute 0 area to the grand total, we still return false. It is not the case that the point P is located strictly inside, and again, by being careful with our analysis, we can even print out or return, if you will, precisely which vertex the given sample point P coincides with, with which vertex of the given triangle the point P coincides. Finally, we come to the fourth case, and the most interesting case is the case when the area of the given triangle ABC is precisely equal to the sum of the areas of the smaller or sub-triangles in this case, and none of the sub-triangles here I designated as sub I, where I varies over 1, 2, and 3 is equal to 0. This is the happy path scenario. This is the only case when we return true from our algorithm, saying that yes, it is the case that the point P is located strictly inside of the given triangle ABC. Again, the proofs of the statements are evident because these proofs revolve around the idea of partitioning a given planar region with into other smaller regions that cover or tile that region of interest tight with no gaps and no overlaps. And once the mathematics behind this idea, behind this algorithm is understood, implementing this algorithm in code, for example, also becomes very straightforward theoretically. Why? We use the so-called Heron's formula that we already proved on this channel in the corresponding episode. And according to this formula, the area of a triangle ABC, planar, non-degenerate Euclidean triangle in the interesting case, is the square root of the four-factor product S, where S is the semi-perimeter, the length of the side A plus the length of the side B plus the length of the side C divided by 2. And that semi-perimeter is multiplied in succession by the following differences between the semi-perimeter and the length of the side A, the length of the side B, and the length of the side C. We also know how to compute the length of all the sides A, B, and C based on the formula that we saw in the previous segment. That is technically one of the ways to supply a so-called Euclidean metric actually in 2 space. In 3 space, we will throw another z coordinate. But that is straightforward to understand. That algorithm does not require much specialized mathematical knowledge. And once the distances between the vertices or the lengths of the sides, for example, A, C, and B are computed, the rest is smooth sailing again. Intellectually, not much effort is going into understanding or generating this algorithm. However, again, the question is how Turing machine friendly that algorithm is, and the answer is not very friendly, even though it is straightforward to generate and understand. The underlying mathematics is very straightforward, precisely because into the real-time path we will have to inject quite a few square roots. We need to compute or use square roots to compute the length of each side, and then we will need to use the square root for the 4th time in order to compute the area of what? The parent triangle, and then the areas of all the smaller or sub-triangles, if you will, the triangles APC, CPB, and BPA, and then run the analysis and write careful if statements. And again, here, because these numbers will be again either the floating point or double precision, the exact tests are fraught with danger in computer programming. They are never done with a direct comparison when it comes to floating point arithmetic. When the data type is float, for example, in the C programming language, or double, we still need to introduce a small real number, plus minus delta, and the size of this delta depends on our tolerance, how precise we want to be with our detection algorithm. So that is again the second obstacle toward this algorithm being Turing machine friendly. Bottom line, the takeaway from this discussion is the following: this algorithm is straightforward to comprehend, generate, implement, but it is not very Turing machine friendly precisely because we have to deal with 2 issues: injecting the square root function into the real-time path, and perform floating point comparisons. The actual algorithm for detecting whether a given point is located strictly out or strictly inside of a given non-degenerate planar Euclidean triangle ABC that we will discuss in great detail and which is the subject of this episode is based on again a middle school geometry curriculum idea or a notion of an equation of a straight line in a chosen Cartesian coordinate system that passes through two given distinct points A and B. The point A has the coordinates xa, ya. The point B has the coordinates xb, yb. The 2 points are distinct, and through these 2 points we construct a straight line in the chosen coordinate system where the points A and B have the shown coordinates. Then the equation of that straight line that passes through these 2 points in the chosen coordinate system is shown over here, and the question is, as it is in the shown form, is the formula shown here Turing machine friendly? The answer is no, it is not Turing machine friendly because it contains the potential division by zero if the two given points sit on the same vertical and thus have the same horizontal displacement from the origin. Then the coordinate xb will be equal to coordinate xa. The difference will be zero. Division by zero will result in a core dump, in a segmentation violation right away. Thus, in order to remove this Turing machine unfriendly shape or factor in our equation, we multiply both sides of this equation by this difference, xb minus a minus xa. We keep the x minus xa portion where it is on the right hand side. That part is shown over here, and then we subtract ay from yx and multiply it by this difference over here. Again, just to make sure that we understand, the difference x minus xa times this difference yb minus y is cleared of the denominator, and it's shown over here, x minus xa, x minus xa, yb minus ya, yb minus ya, minus ya brought over the equal sign to form the difference y minus ya times that denominator xb minus xa. The whole thing is carried over the equal sign and is equated to zero. And the interesting thing is this: in middle school and in high school, the most that students work with and think of is the proverbial function y of x. But here in this shape, we can think of this expression over here not as a function of x for the symbol of y, but as a certain function f of two real numbers, x and y. And in this case, this equation right here, for this part, can be thought of as a function of two variables, x and y. And apparently, as it turns out, this function can take on only three distinct values that are of interest to us. That function can be strictly less than 0, equal to 0, or strictly larger than 0, depending on which values x and y are inserted into that part of the equation. That is, it should be evident that any values of xy that correspond to a point that belongs precisely to that straight line, for example, this point right here, will have the numbers x and y such that when these numbers are plugged in into the site, they will produce a true identity. 0 on the left hand side of the equal sign, 0 on the right hand side of the equal sign. So this expression over here will collapse into 0 if x and y correspond to the coordinates of any point that belongs to the given straight line. And the interesting in its own fact from the mathematical standpoint is that any point that does not belong to the straight line, whose equation we show over here, and the one that sits, for example, over here or over here on one side or the other, will generate for our function of two variables now either the real number that will be strictly less than 0, or a real number that will be strictly larger than 0. And in the study of analytic geometry, there is a corresponding theorem which basically says that the straight line thus constructed partitions the plane into two half planes that have precisely the property shown over here. And at this point in our episode, the next few deductions will be optional. These are for curious travelers only who want to understand why the upcoming algorithm does work and how does it work. And the impatient kind can skip forward to the next segment. Here we observe the following. Let us say that instead of working with this expression, which has admittedly a lot of information, usually in the grown-up mathematics, in the study of analytic geometry, we work with a slightly more generic expression, which looks as follows. Ax plus by plus c is equal to 0. It is claimed that this equation of first degree over two symbols, x and y, defines precisely a straight line in the corresponding plane in an appropriately chosen coordinate system. And that coordinate system actually does not really have to be orthogonal. It is perfectly fine for the coordinate axis, in this case, to form an angle that is not necessarily right. Let's say we have our coordinate system that looks like this: x, y, 0. We have the direction vector ex shown over here, the direction vector ey shown over here. There is unit distance shown for every axis, and let us say we have a straight line that passes through this coordinate system in some way. Doesn't really matter. The idea is that this straight line, whose equation in the interesting non-trivial case will be depicted precisely by this expression, you will separate the entire parent plane into two half planes, for which our function of two variables over here will precisely have this property. Any point on that line will generate 0, and any point that is not on that straight line will generate a number that is either less than or greater than 0. And the proof of the statement is the following. Let's say we take a point that is strictly off the straight line that is shown in blue, and let's say this point is located over here. Let's say this is our point P. How do we generate the proof that that point will generate the number that is less than or equal to 0? Well, the basic idea here is the following. We construct a straight line that is parallel to the y-axis. You see, parallel to the y-axis. That straight line will intersect our line at a point over here that we will say, let's say we will give a name L to this straight line. This point will be PL, the point that belongs to that straight line. At what will be the coordinates of the point PL? Well, the point PL will have the following coordinates. The x coordinate of that point will be precisely the x coordinate of the given point. And let's say this point has the coordinates x0 and y0, just for the sake of argument. Then our point PL will have what? Will have the x0 as the same coordinate, for the same coordinate as the given point, and its y coordinate will be some number, let's say YL. Then what can we say? How can we spin this expression to our advantage? Well, let's take a look. Let's assume first that the real number b is definitely not 0, and let's say it is strictly larger than 0. Then what can we say about the relationship between the numbers YL and Y0? Well, we say that Y0 in our case is strictly larger than YL. Would you agree? This precisely captures the idea that the point P is not on the straight line L. It can be here in this half plane or in this half plane, it doesn't matter. Let's say it's over here. So in this case, for our pictorial representation, this is the case. If B is greater than 0, we multiply both sides of this expression by a strictly positive real number, B, times B. These things do not change. And then what do we use? Well, this is technically not exactly middle school or high school material, but it's not difficult to comprehend. This is one of the properties of real numbers. If we add to a given inequality one and the same real number, the inequality will not change. So to either side, we add plus ax plus c, and here we will do which x. We will take precisely x0, and we will take precisely here again plus a times x0 plus c. You see what is going on? YL times b plus a x0 plus c is less, in this case, is less than the expression shown over here. But the whole idea of this maneuver was to do this, to do what? To make sure that this point P belongs to the straight line L. And once that point belongs to the straight line L, what happens? Then this expression becomes precisely equal to 0. This is the part that we're looking for right here. So this is 0. But then in our case, what do we have? A, let's say, x0 plus b y0 plus c is strictly greater than 0. See, if we put this f at xy associated with this expression, we get precisely, in this case, greater than 0. Now, as an informal exercise, I suggest that you move this point on the other side and run the similar analysis and see what will happen when y0 will be less than yl. B is 0, multiply, what will you have? In the end, exactly, you will have less than 0. You will not get 0. You will have a number that is less than 0. And in the second case, where you will say, okay, what will happen when b is less than 0? This number is less than 0. Exactly the same thing. You will take your initial inequality, y0 greater than yl. You will multiply it by a real number, b, that is less than 0. You will then flip that sign, and then in this case, this inequality will flip. Will be less than 0 and greater than 0. Game over. Proof is complete. If you have any questions, use the comment section below. But again, yes, there is a little bit of grown-up analytic geometry, official analytic geometry going on, but again, this is not very intellectually demanding. Any motivated upper middle school, lower high school student should be able to comprehend this. And the main takeaway from this proof, we recommend that you work on this proof some more and prove to yourself these inequalities by using these manipulations and paying attention to what is going on right here, here, and here, and using our idea of a parallel line to the y-axis idea, and prove to yourself that this is really the case. This is really the case. This is all three possibilities that exhaust anything that can happen in the given plane with respect to any point that is located in some way in reference to the given straight line that passes through two given points A and B. And now we go back to this expression, and we now start paying attention to the direction in which we use our computations. From A to B, versus, for example, B to A. And in order to understand what is going on with this direction and being sensitive to which direction we work with from A to B or from B to A, we carry out the following sample computations. For demonstration purposes, let us assume that we have chosen an orthogonal or a Cartesian coordinate system with the x for the horizontal axis, y for the traditional vertical axis. These two coordinate axes intersect at the point O. We call that point the origin of our coordinate system. The scale of 1 unit of distance along the x-axis and 1 unit of distance along the y-axis is shown. Now we have a legitimate coordinate system. Let us say we have two sample points, A and B. The points are distinct. In the chosen coordinate system, they have the following coordinates. The point A has the coordinates 2 along x, 1 along y. And the point B has the following coordinates, 6 along x and 2 along y. The point A, the point B. Moreover, let us say that our sample point P does not belong to the straight line which passes through the points A and B, and let's say it has the sample coordinates 4 along the horizontal axis and 3 along the vertical axis. Now, we're usually, again, in middle and high school, we're not that attentive to which order we use in order to form this or that geometric object, but now we want to pay attention and prove to ourselves that that order in some sense does not really matter. And we prove it to ourselves as follows. When we say that the straight line shown over here, the equation of a straight line that passes through the points A and B is given over here, we will take it to mean precisely that the direction in which we look in this case at this point is from the point A, which is the origin, into the point B, which is the destination or the terminal point. And in that case, once we do our manipulations of clearing the denominator, avoiding division by 0, running away from a core dump and segmentation violation, we have a nice expression that is Turing machine friendly. This is the specific order in which the indexes, which designate which point is which. This is precisely how we will treat it. As such, when we insert into our equation shown over here, the free variable x and y will now take on the values of the coordinates of the point P, which I designated here with xp and yp. This is a very straightforward maneuver. Our free roaming point in the xy plane now takes on an identity, and that identity is what is the point P as is shown by the subindexes xp, yp. And we simply compute the value of this function. Remember the uppercase f of xy, and in this case uppercase f of xp and yp. We plug the numbers that we have, the sample numbers shown on the right hand side of your screen, into the formula, and we obtain 4 minus 2 times 2 minus 1. This is what 2 times 1 is 2, and then 3 minus 1 times 6 minus 2. This is 4, this is 2, this is 8, and 2 minus 8 is negative 6, but the actual value itself is of no interest to us, is the fact that the number is strictly negative. You see, strictly less than 0. This is the important takeaway from this sample computation and sample demonstration. And now we want to keep the direction from point A to point B the same, but now we want to move the point P, the sample point P, that does not belong to the straight line that passes through the points A and B, to the other half plane, because now we already know, based on the previous theorem whose proof we constructed in the previous segment, the straight line that passes through the points A and B exactly partitions the given plane into two half planes. In the next computation, we will move the sample point P, logically speaking, below the straight line A, B, even though, again, the different words that we use to describe the location of the point P with respect to the line segment AB could be anything. For example, in this case, when we direct our gaze from the point A toward point B, we can say that in this case, when we have the negative value for our function shown over here, we can say, for example, that the point P is located to the left of the line segment AB. And in the next segment, we want to see what will happen if we will move our sample point P to be located in the other half plane, into which our straight line that passes through the points A and B partitions the parent plane. Now, for the next experiment, let us assume that the sample point P is located in the other half plane, into which the straight line that passes through the given fixed points A and B partitions the parent plane. And let us assume, for demonstration purposes, you are more than welcome to pick different numbers. Don't pick the numbers that I have. The point P has the coordinates 5 along the x-axis, 5 along the x-axis, and 1 along the y-axis, 5 and 1. Now we go back to our original formula, and instead of plugging in the numbers that we used in the previous segment, now we plug in the numbers 5 for the x coordinate and 1 for the y coordinate of P1, and 5, 3, and 4 before. And we compute the result of our function uppercase F of 5 and 1 in this case. What will we have? 1 minus 1 will be 0. 0 times 4 is 0. Here we have 2 minus 1 is 1. 5 minus 2 is 3. 3 times 1 is 3. So we have positive 3. And the number here, again, what's important is not the actual value 3 for us, but the fact that this number is strictly positive, as we expected, because the theorem, as long as the proof is correct, and the proof is correct, precisely predicts that. But we want to touch with our hands, so to speak, the theory and play with numbers. You can pick a different number for your experimentation purposes. But what is the important takeaway from this experiment? Well, the important takeaway from this experiment is the following. Which names we use to describe the location of the point P, sample point P, with respect to the given straight line that passes through the given points is irrelevant. Could be up, down, left, right, or whatever other words we will find to describe this location. The important thing is that the sign, you see the sign over here, use green, the sign of the expression that we obtain once we plug in our specific number changes to the opposite. In other words, the signs in our expression disagree. One is positive and the other one is negative. Now let us investigate what will happen if we will direct our gaze from the point B to the point A. Remember that now, since we are sensitive to the direction along which we travel over the straight line that is given to us, or we're sensitive to the order in which we use the lettering in the description of the equation over here. The top equation I left as is, but here we want to now swap the roles of the points A and B to their opposites. In other words, where the point to B used to be A, it now becomes B, and conversely, wherever the point used to be B, now it becomes A. And I made the corrections here in the equation below What used to be A became B. What used to be B became A over here, uniformly along the entire equation. The structure of this equation remains the same. The only thing that changed is the order of the points A and B. Now we travel along the straight line that is defined by the points B, A in the direction from B to A, or we direct our gaze in such a way that it originates at the point B and terminates at the point A in this direction. And we run essentially the same numbers. First, for the point P that is located in one half plane, into which the straight line through the points A and B partitions the parent plane. The coordinates of this point are shown over here, 4 and 3. We go back to our equation, and instead of xp and yp, we slug in 4 and 3. Carefully plug in the numbers. This exercise is trivial. It's literally nothing beyond middle school arithmetic, and we compute the result. The result comes out to 2 plus 4 comes out to be 6, positive 6. And the important part that this time, the result of our expression, or the function uppercase f of xp and yp, or of 4 and 3, came out to be positive. Again, depending on how we want to look at the words with which we describe the relative position of the point P with respect to the straight line AB, we can say it is located on top or above, or if we look from the point B towards the point A, we can say that the point P is located where? To the right of the straight line that runs from B to A. And in the next experiment, we will compute the value of our expression shown over here for the point P that is located in the other half plane into which the straight line through the points A and B partitions the parent plane. That is, if we move our sample point P into the opposite half plane into which the straight line that passes through the given points A and B partitions the parent plane, we take the coordinates of that point P, 5 along x and 1 along y. We carry these numbers into our formula shown over here, where we swapped the roles of the points A and B. We now move along the straight line through the points A and B from the point B to the point A. The B is origin, A is the terminal point. We slug these numbers into this formula, and we again do straightforward arithmetic. The number in this case comes out to -3. And you guys should keep me honest, verify. Maybe I made a mistake somewhere, but again, it doesn't really matter much the specific numbers that you play with, because we deduced a theoretic result. We knew already going into this practical exercise, we knew what to expect. The theory said so, but once we marry or join a little bit of practice with a little bit of theory, we understand better both the way the theory works and the way the practical situation applies to this theory. And again, what do we see in this case? We see in this case that once we move the point P to the other half plane, even when we swap the roles and we're now sensitive to the order from B to A, the transition of the point P, sample point P, from one half plane to the other causes again precisely what? The change in the sign. -3 is now strictly less than 0. +6 is greater than 0. Again, we can use different words. We can say the point P over here, with which we associated the negative value of our function, uppercase f of xy, is, for example, below the straight line A, B. Or if we move from the point B to the point A, then we can say that in this case, the point B is to the left of the straight line that passes from B through the points from B to A, and so on. But again, the words that we attach to the qualification of the relative position of the point P with respect to the given straight line, they do not really mean much to us as long as, and this is the key and the crucial aspect of the algorithm that we are about to uncover, the fact that the sign of the function to which we referred as, where should I write it? F, uppercase F of x, y, changes from one to the other, to the opposite, from positive to negative and from negative to positive. And the final word, some of our viewers can say, Roman, you're shuffling the symbols willy-nilly left and right. Originally, you gave us official analytic geometry, highbrow equation this. You work with the middle school version of it here. What is going on? Well, it's very straightforward. You should see that if you multiply out this equation and torture all this, opening up the parentheses, and then collect the like terms, you'll have precisely the equation that is used in the grown-up analytic geometry courses. For example, when we multiply x by this parenthesized expression over here, yb minus ya, it becomes precisely what? With a negative sign, it becomes uppercase A, game over. What is b? Well, we walk along this expression, we see y times this parenthesis, xb minus xy, taken with the minus sign, boom, it's b. And what is uppercase C? Constant. Well, xa is a constant number. This difference is a constant number, so multiply this xa by this difference, and then what do we do next? To that number, we add another constant, ya times this difference. That's also a constant number. Glom these constants together, it becomes our C, game over. So either way, our function uppercase F of these two real numbers, x and y, they figure prominently into our equation of a straight line in a chosen coordinate system, changes its sign when a point that roams our plane hops from one half plane into which our given straight line partitions the parent plane into the other. Now that we understand how the mathematics of this idea works, we can now give a somewhat official name to our function uppercase F of x and y. And now is the prime time for our function, so somewhat mysteriously called uppercase F of x and y, to come out of the shadows and earn a name that we can agree on. For example, it doesn't have to be, but my suggestion is we can call that function the location predicate of the point P with respect to the points A and B, taken in that order, A and B in that order. We can capture it in symbols as uppercase L. P is the point whose location is tested with respect to what? Straight line that passes through these 2 points, color-coded. And that expression over here, you know by now, you understand what is going on, where did it come from, and why this algorithm works. And the final leg is constructing the actual algorithm, which by now you should be able to do on your own. You do not need me. So what do we do here? Well, we, let's say, fix the side of the triangle AB and the implied straight line that passes through these points. How many points we have to work with? 2, exactly. The point P and the point C. Are these 2 points on the same side of the straight line? Yes or no? And how do we find out? Well, we compute the location predicates for both of these points. We already know that. And regardless of which silly names we use, left, right, top, bottom, above, below, it doesn't really matter, as long as the values of their location predicate agree on the sign, then evidently, by our theorem that we proved, they must be on the same side of the straight line AB. How do we capture the same side programmatically, or if the value of the predicates agree? Well, we compute one predicate. We know how to do it over here. LPAB of the point P with respect to the points A and B. LCAB of the point C with respect to the points A and B. C with respect to the point A and B. And we simply construct a product shown over here. LPC. This is the product of this location predicate LPAB times the value of the location predicate CAB. If these values have the same sign, both positive or both negative, what will happen? Well, the value of this product will be positive. And if the location predicates disagree, one positive, the other negative, or one negative, the other positive, the product will be what? Negative. There you go. Problem solved. Algorithm constructed. What do we do then? We floss, rinse, repeat. We now go, for example, counterclockwise. We fix the side BC of our triangle. How many points we will have left? 2 again, P and A. And we ask the same question. Do the points P and A are located on the same side of the straight line that passes through the vertices B and C? And how do we do that? Location predicate PBC of the point P with respect to the points B and C. Location predicate of the point A, B, C of the point A with respect to B and C. Construct their product and do the same thing for the final side. Side CA, once this side is fixed, how many points we have left to play with? 2, P and B. We do the same thing. We compute the location predicate PCA of the point P with respect to the straight line that passes through the points C and A. We compute the predicate LBCA of the point B with respect to the straight line that passes through the same C. Same points, same points, same points, same points, same points, same points here. We construct the product LPB, which is location predicate of the point P with respect to the points C and A times the location predicate of the point B with respect to the points C and A. That's it, game over. Then we construct one compound if statement if the location of the points BC relative to the what needs to be relevant is greater than 0, greater than or equal to 0, then and the value of the location predicate of the points P and A captured over here is greater than or equal to 0, and the location of the points P and B relative to the points C and A captured over here greater than or equal to 0, then we return inside. The point is inside. In other words, our location predicates of each pair of points with respect to the corresponding side, they all agree on the sign. That means that the sample point P is inside. Return inside. Otherwise, if this compound if statement fails, otherwise return outside. Game over. Straightforward algorithm in all respects. Straightforward to comprehend, straightforward to construct, and straightforward to implement. And here is a sample implementation of our algorithm in the best programming language of all times, or C. That is, here is a simple, heavy lifting only implementation of the algorithm that we discussed in this episode using the best programming language of all times, C. In general, you will include the standard I/O header. You will define a structure that will be a point. Here I use, again, for reference purposes, int, but in a realistic application, of course, depending on your tolerance to the precision that is required in your situation, you will use either float or you will use double over here. Again, the burden of doing this replacement is on you. This is just the, like I said before, heavy lifting, the gist of it. You define a structure, a data type that will carry your point. You define a data structure that will be your triangle, which will be defined in terms of a point. we have three vertices, vertex A, vertex B, vertex C, type def, struct, point T underscore TVA, and so on for the remaining two vertices. Then we implement a function called location predicate. It takes the pointer to the point P that we need to compute the location predicate for, and the points with respect to which we compute the location predicate. And again, the order here is important. First is this point, second is this point. You understand the underlying mathematics, and the underlying mathematics is translated into the relevant C code verbatim. Pointer reference and then consequent fields. Already you understand what's going on here. You return that location predicate, and in the main function called point in triangle, it returns integer. Again, it returns true when the point was detected to be in the triangle, and it returns not true when the point is not in the triangle. The interface to this function is quite simple. You can do it anyway. Pass triangle first, point second, or point first, triangle second, up to you. Pointer here, and again, here I only show a partial implementation. You roll through basically what you do in C, what we discussed before at the algorithm of pure computer science algorithm level. You construct the location predicate for the point P with respect to A and B. This is the syntax. You do the same thing for the point C with respect to points A and B. This is the syntax. The pointer comes in here P directly. The other addresses must be passed by hand. Ampersand, ampersand. Then you construct the product of these two, put them in a product, call it PC, and you do the same thing for the remaining sides, BC and AB, BC and CA. You have three integer variables, LPC, LPA, LPV, shown here and here. You test them in the compound if statement for greater than or equal to 0 and greater than or equal to 0 and greater than or equal to 0. If this test succeeds, we return 1, meaning yes, this point is in this triangle. Otherwise, we return 0. The function terminates, and the code that I do not show here, for which this includes standard IO header, will work as your traditional extern int main, int argc, char star argv array, where you pass the arguments to your function. You create the sample point with initialized with certain coordinates. You create your triangle initialized with certain coordinates, and then you invoke the routine that we show over here, the function over here, by passing the address of your sample point and the address of the sample triangle. Printf, the return value. You can use a tertiary or ternary operator. If the function returns true, you print in. Otherwise, you print out side of the given triangle, and then you print the triangle itself, the coordinates of every vertex. Now, this is it for the computer science part of this episode, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics, S3M for mathematics 7, the problem number 7 in mathematics for our third season. And the challenge in this problem is the following. Given a so-called binomial differential, which has the following shape: a constant number A plus a constant number B times a, let's say, real number Z raised to the power of P times Z raised to the power Q dz, where the integration is carried out with respect to the variable z, and z, where a and b are constant real numbers, and p and q are rational numbers. The challenge here is to invent or discover, concoct, generate, construct a way to evaluate these integrals and obtain a synonym expression hopefully as a finite combination of elementary functions that will be a function precisely of these two numbers p and q, and of course the numbers a and b. But here again, remember the numbers a and b are constant, and as a hint, the main characters in this challenge will be the rational numbers p and q. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the problem S3E11.